increase, in fact, the tension of the membrane, what we see is that we see spikes. We see actin that polymerizes and is able to push inside the membrane. So this really looks like cellular philopodia. The other way around, of course, because philopodia are outwards. But so we can reproduce this philopodia, and we can look at the time at which it grows. And this was modeled in another system. So it's because this branch actin network is able to have some branches that escape and don't, are able to push the membrane just by pure polymerization. And in fact, if we change membrane tension, we have this occurring, so it's completely different. Now we have tubes that are able to be pulled by the actin network here, because we have a stress that pushes inwards, and it's able to pull tube out of the membrane. So this could mimic endocytosis, of course, again, the other way around. But one advantage of this outside geometry, compared to the inside geometry I presented before, is that we can change the ingredients very much more easily outside with this experiment. So now I'm finished. I would like to conclude that cell motility can be mimicked to be studied in controlled conditions and with lots of applications, from medical application to finding generic models that can explain all that. And I would like to thank all the people who did the work. This couldn't work without these people in the team, but also with lots of collaborations, and also, as you said, Mike Merle, who was a great add in our lab when he was a postdoc, and it was a pleasure having him. And also Laetitia Pontani, who was the golden hand girl, who was able to have the system inverted emulsion work, and Karine Gevorkian with the membrane. Thank you very much.
Great, we have time for lots of discussion. Yes?
Hi, there's been a flurry of activity in simulating active systems.
Oh, thank you. So with all the capability that we have with modeling polymerization and motor-driven actin motion, where is the need for theory and simulation to help understand these systems, to complement the experiments?
Right. Well, in general, or?
Specifically for the experiments that you described.
All right. So, for example, this one. The last one. So we're trying to think about what happens. So why do we have in some conditions the membrane going inwards? I mean, the filament is pushing the membrane inwards. So I think the need here, the need here is to be able to mix organization of filaments with random organization of filaments. So this is an example, I think. So I'm just talking, I mean, it's very new data, but here the filaments are oriented, they are parallel, not even anti-parallel. What we think happens is that, so you have the barbed end, so the growing end that is towards the membrane, and it's able to push the membrane inwards. Whereas here, they are randomly oriented, I think, because otherwise, how could you pull tubes outwards, right? So how can this happen? Either by polymerization or by addition of motors, that these filaments reorient, and from a random structure, give a parallel or an anti-parallel structure. So for example, I think that during division, there is this cytokinesis ring. So during division, you have a network that is completely randomly oriented. And then at some point, you have filaments that orient anti-parallel so that myosin motors are able to contract them. So how does this happen? That randomly oriented network becomes anti-parallel oriented.
It sounds like an isotropic pneumatic transition.
Yeah, exactly. Exactly, absolutely, yeah. So what makes it transit from one to the other?
Thank you.
And how can we, so is it the length of the filaments that matter? Is it their orientation, the concentration? What's that? So this is the big question we would like to get, to get directions to look at it.
Thank you. I look forward to talking with you about that.
And I just wanted to know how the pressure in the cell can affect this process.
The pressure in the cell?
Or outside, I mean, just for curiosity, how the
Right.
pressure can affect.
So the cell is very different from our systems because there is a reservoir of membrane. So as soon as the cell feels pressure, there is a mechanism that will bring new membrane or remove membrane so that the cell doesn't feel it, right? So the only pressure we can, so do you talk about mechanical pressure or osmotic pressure or both?
Could be any.
Okay, so osmotic pressure, so it's a way of changing, we change the concentration, then the cell wants to increase or decrease its volume depending on the concentration outside. So this pressure works on the membrane, right? So this would push the membrane inward or outward, but then there will be a reaction inside, which is not the case in our systems, to increase the concentration, I mean, to react so that the cell goes back to its initial state. In fact, osmotic pressure treatment is used in cells to look at the role of membrane tension, right? But you should look in the very early times, otherwise the cell will adapt. Now the pressure, if you put the mechanical pressure on the cell, you want to look at the mechanics of the cell. So this is done by AFM, by microplate squeezing, and this will give you the whole mechanical property of the cell. I mean the whole modulus, not the modulus of one network or the other.
So, I mean, in general, it just can affect the movement of the cell.
Nobody knows this, but for sure, if you push on a cell, you will have it react, and it will push on the other way, right? So if you squeeze a cell, it will want to expand, because the motors will be more active. It will activate the motors. This has been shown quite extensively. So you could, if you would push a cell. So that's right. So I didn't go into the details, but the cortex. So in fact, the cell uses two ways of moving: either the lamellipodium, as I showed you, or the squeezing mechanism. And when it's squeezed, it's more the squeezing mechanism that's at work. If you have an infinite cover slip, it will be the lamellipodium that will drive the cell, right? So it's true that now we know that if you put the cell in narrow channels, it will move faster, but with a different mechanism, with a squeezing mechanism rather than the lamellipodium pulling.
Yeah, and then,
That was super interesting. Just going back to one of your early movies.
Where are you?
I'm all the way over here.
All right.
Hey. When you saw the shell of actin expand and then crack,
Yes.
I was actually surprised to see that it sort of unfurled. And I was somehow expecting to see that it would maintain the curvature as much as possible, because it had been formed with a small radius of curvature. I was wondering if you could comment on the physics of that.
So, in fact, I would have expected exactly the opposite, that it would relax and be flat.
Well, it started out as a very curved object.
Yeah, but it's under stress.
Yeah, but it's also cross-linked with, I mean, you know, if I did poured rubber or something in that, and it was stressed, it would not want to shear to straighten out if it was formed in the shape of a sphere. So
Yeah.
I don't know the answer.
Okay, I see what you mean.
Yeah.
I think it's a bit of both, because it was curved, but the outside, so the outside layer is the one that is most under tension, and the inside layer is not under tension, right? So what we see at the end of this movie, I guess, this is what you meant. This, yeah, right?
Mhm.
This is, your point is that this is still, I mean, in between curved and flat, right? Well, I interpret it in terms of layers. So each layer is bound to the other, but it's always produced here at the surface that is not under stress. So when it breaks, it's here it's under stress. The thing that was not under stress here, under tangential stress, I mean, is now under stress because this one here wants to expand.
Yeah, I was just wondering if you could understand that final shape in terms of.
No, we didn't. We were surprised. We were expecting to see a flat shape, but I see your point. This one was curved at the beginning, but so I guess they can shear between layers. But I never looked at this. We can discuss it.
I think Hamza, and then I think one last question back there. Sorry, Hamza up here. Sorry, up here. Sorry, thank you.
So you showed that endosome that was created by the actin filament, and I had a general question about being transported by the actin versus myosin 1, myosin 5, something like that. Is there an
Sorry,
Can't
apparently
hear.
the microphone's not
Can we
working.
change the mic?
Let's see, so maybe
There's another mic.
Can you hear me?
for that microphone.
Okay, so there was a movie in which the endosome was carried by the actin network, and you said there's no motor involved here. So my question is, in general, is there an advantage being carried by the actin filament, and how does it compare with actively transported by this myosin 5, for example?
All right. So, well, I think the cell has the whole mechanisms that are available to move. And in fact, the ones I showed you, the endosomes carried and propelled by actin polymerization, were forced to do that. I mean, the cells were depleted in whatever, so that we can see that. So it seems that at the beginning of endocytosis, this actin dynamics is very important. Not for the long distance transport, but for the production of the endosome. So there is a squeezing of the actin at the collar of the endosome, and then it seems that because there is lots of activator there that are squeezing, it seems that the endosome can keep this polymerizing activity, and then kinesin motors of myosin 5 take over, right? So it's more at the first moment of endocytosis that actin seems to be very important, and this was forced to happen.
And final question right here.
Hi, Cecile. Going back to the initial picture of the cell that has a migrating cell that has all the actin on one side, on the front, let's say, and myosin at the back. Do you, maybe you said that already, but I didn't get. Did you ever observe in your reconstituted systems that actomyosin mixture organized like that? So, for example, let's say all the actin, one part of the vesicle and the.
I removed a video for this talk. I think this will illustrate your question. This is in cells, so these are keratocytes. These are fragments of keratocytes. So you see there are, as I said, well, there are leaving the scale here, the fish scale here, fish scale that's here, and you see they move and they make long branches and all that. So if you treat these cells and get fragments of those, I'll show you a movie that, so at the beginning you have something symmetrical, so in red you have, so it's not at all my work, it was done by Lakoski and Borisi. So you have myosin motors here in red, and actin filaments that are able to polymerize all over the place, and especially at the membrane. So at the beginning you will have something symmetrical with actin polymerization occurring all over the surface here. And if you make a push, you will concentrate the actin filaments and the motors, so it answers your question. You will have antiparallel, you will provide an antiparallel structure just by pushing like you would push a Mikado plate. You know this Mikado plate. You push it so there are antiparallel. And then the motors will be more efficient. We guess, I mean, it's a phenomenological explanation. And what you will see is that this will contract, and you will have a steady state. Then this side will decide to do actin polymerization, and this side will decide to contract. So look at it. Ready? So you have the spherical fragment, the symmetrical fragment here. You push it, and you see it's able to move. Actin polymerization here, myosin contraction here, right?
So just that simple push breaks.
Simple push will decide where the myosin will be more active in contracting than actin polarization will be in pushing.
Okay, well, thank you for a beautiful talk.